Hello, gentle listener. Welcome to Pets for Sleep. Whether you have returned tonight or are discovering this quiet corner for the first time, this is a place to slow down, learn something gentle about the animals we love, and allow the day to soften around you. Tonight, we are following 100 relaxing facts through the life of the domestic cat. Perhaps there is a cat resting somewhere near you now. It may be folded into a small circle on a blanket, stretched across the end of a bed, or balanced on the narrow back of a chair. From a distance, very little seems to be happening. Its breathing is slow. Its paws are tucked beneath its chest. One ear may turn briefly toward a distant sound, and then settle again. Yet almost every part of that quiet animal carries a much older story. The domestic cat's scientific name is Felis catus. It belongs to the animal family called Felidae, which also includes lions, tigers, leopards, lynxes, servals, and many smaller wildcats. A house cat is not simply a tiny lion. Each living cat species has followed its own evolutionary path, adapting to different prey, climates, landscapes, and ways of life. But members of the cat family still share many recognizable features. They have forward-facing eyes, sensitive ears, padded feet, curved claws, sharp canine teeth, and flexible bodies made for sudden, controlled movement. Even a cat sleeping beneath a kitchen table is carrying the basic equipment of a small predator. If you enjoy these quiet journeys through the lives of animals, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight, or which pet is nearby as you listen. It helps other animal lovers find their way to this calm corner of the world, one sleepy companion at a time. Among all the members of the cat family, the domestic cat has formed the widest and most lasting relationship with human homes. People have occasionally raised or tamed individual wild cats, but that is different from domestication. Domestication is a long process in which a whole animal population changes across many generations while living close to people. Modern domestic cats descend mainly from a branch of African wildcats known as Felis libica. These wildcats still live across parts of Africa and southwestern Asia. They have sandy or grey-brown coats, dark markings on the legs and tail, long limbs, and a body shape that can look surprisingly familiar beside an ordinary striped house cat. The exact beginning of cat domestication is still being studied. For many years, the most common story placed its early stages beside the first farming settlements in the Near East. Stored grain attracted mice. The mice attracted wildcats. People benefited from having skilled rodent hunters nearby. That explanation is still important. But ancient bones and newly recovered DNA have shown that the full journey was more complicated. Some cat populations may have moved with people at different times, along different routes, and from different regions around the Mediterranean. We will eventually follow that history through early settlements, islands, trading ports, and the Roman world. For now, the important point is that humans did not completely redesign the cat. Most pet cats still resemble their wild relatives in size, body shape, senses, and basic behaviour. Humans later created breeds with unusual coats, shortened faces, curled ears, or very long hair. But most cats living in homes do not belong to a formal breed at all. They are often described simply as domestic shorthairs or domestic longhairs. Those names usually describe the coat rather than a carefully recorded family line. This makes the average household cat part of a broad and genetically varied population. Two cats with similar markings may have very different bodies, habits, voices, and reactions to the same room. One may spend the afternoon watching birds through a window. Another may sleep until evening and become active when the house grows quiet. Cats are often described as night animals, but their schedules are flexible. Light matters. Meal times matter. Outdoor access matters. So do temperature, age, play, nearby animals, and the daily movements of the people in the home. A cat may arrive with an ancient set of instincts, but it continually adjusts those instincts to the place where it lives. That balance between old biology and present experience will appear again and again. It is there when a cat listens behind a wall, investigates a new scent, learns the sound of a food container, or chooses the same sleeping place each evening. The quiet animal resting nearby is therefore not simple or inactive. It is a flexible member of an ancient hunting family, carrying wildcat senses into a human-made world. And when it finally rises, stretches its spine, and places one front paw against the floor, the first hidden detail appears. A cat does not walk on its feet in quite the way that we do. As the paw settles onto the floor, only the front end of the foot meets the surface. A cat is a digitigrade animal, which means it travels mainly on its digits or toes. The heel stays raised behind the paw instead of pressing flat against the ground. Humans use a plantigrade stance, placing the heel and much of the sole down with each ordinary step. Keeping the heel elevated lengthens the cat's working limb. That added length supports a quick stride while allowing the body to remain low and controlled. Fur hides much of this arrangement. What looks like a backward bending knee near the floor is actually the ankle and heel. The true knee sits higher, close to the body. Each front paw normally carries 5 digits. 4 support the cat during an ordinary walk, while the 5th sits higher on the inner side of the limb. That raised digit is the dew claw. The hind paws usually have 4 digits each, giving most cats a total of 18 toes. Some cats are born with extra digits through an inherited variation called polydactyly. Their broad paws can look like mittens, although the number and position of the extra toes vary. The dew claw rarely touches level ground during a calm walk. Its higher position becomes useful when the cat grips a toy, holds food, climbs a rough surface, or pulls an object closer. At the end of each digit rests a curved claw. During relaxation, the claw lies partly within a protective fold of skin and tissue rather than scraping across the floor. Elastic ligaments help hold it in that resting position. When the cat tightens flexor muscles in the lower limb, tendons pull on the final toe bones and rotate the claws outward. A tendon is a strong band of tissue connecting muscle to bone. This movement brings the sharp tips into contact when extra grip is needed. Keeping the claws raised during normal walking reduces wear from soil, wood, carpet, or stone. Their curved shape works especially well on surfaces that can be pierced or hooked, including tree bark and woven fabric. A claw does not disappear completely inside the toe. Its tip remains protected beside the final digit until muscle tension brings it forward. Beneath the toes, several dark or pink pads soften each landing. Small digital pads sit under the individual digits, A larger central pad carries much of the load in the middle of the paw. On the front limb, the carpal pad rests higher and farther back, where it usually avoids the floor during a slow walk. It can make contact during fast stops, steep descents, or some climbing movements. These pads are formed from thick skin-covering cushions of fat and connective tissue. When weight arrives, the tissue changes shape slightly. The pad spreads force across a wider area, increases contact with the surface, and reduces the vibration created by a hard landing. Researchers can measure this quiet process with pressure-sensitive walkways. In one study, 4 adult cats crossed such a walkway at speeds between about 0.4 and 0.8 meters per second. Sensors recorded where pressure appeared beneath each pad and how it shifted as the paw accepted the cat's weight. The pads also contain sweat glands. Moisture may appear in paw prints when a cat is warm or stressed, although the paws do not cool the whole body as efficiently as human sweating cools ours. Contact can leave chemical information as well. Glands between the toes contribute scent, and scratching places that scent beside the visible marks made by the claws. The cat continues across the room with its heels lifted, claws protected, and pads changing shape beneath each step. Muscles place one paw after another with careful control, keeping sudden impact and unnecessary sound low. Its quiet movement grows from several structures working together, each handling a different part of the force between body and floor. Above those padded toes, the moving framework becomes even more flexible, allowing the shoulders and spine to lengthen, compress, and turn. Force travels upward from each padded toe into the legs, shoulders, spine, and pelvis. The cat's smooth movement does not come from loose bones. Its flexibility comes from the way solid bones are connected by joints, discs, ligaments, and muscles. Each part moves within a controlled range while the surrounding parts adjust with it. Near the front of the body, the shoulder blades rest along the outside of the rib cage. Muscles hold them in place and guide their movement. Human shoulder blades connect to a broad, bony framework through the collarbones and breastbone. A cat's clavicles, or collarbones, are much smaller and sit within muscle rather than forming the same rigid brace. This arrangement allows each shoulder blade to slide along the chest wall as a front leg reaches. During a long step, the shoulder itself moves forward with the limb. That extra motion adds length to the stride before the paw even leaves the ground. Mobile shoulders also help the chest pass through narrow openings. For many cats, the head provides a useful first test of whether a gap may be wide enough. The shoulders can shift inward behind it instead of remaining fixed at their widest position. Body size, thick fur, weight, and the shape of the opening still matter. So a gap that fits the head does not guarantee that the whole cat can pass safely. Behind the shoulders, the spine continues the same pattern of controlled freedom. A cat has a chain of vertebrae extending from the neck to the tail. Between many of those bones sit flexible discs that cushion movement. Small joints guide how neighboring vertebrae slide and turn. Ligaments limit the range, while layers of muscle bend and stabilize the chain. No single hinge creates the curved shape of a running cat. Motion is shared across many connected segments. As the front legs reach forward, the spine extends and the body lengthens. The rear legs then swing far beneath the abdomen. When the paws meet the ground, Strong muscles around the hips and thighs push the body ahead. A faster stride can make the back appear to open and close like a spring. Before a jump, the hind limbs fold beneath the pelvis. Muscles shorten, tendons tighten, and the joints store a position from which force can be released. The rear paws press against the surface, sending the body upward or forward. Upon landing, the front limbs bend at several joints. Shoulders move against the chest wall, elbows flex, and the pads spread under pressure. This coordinated bending helps absorb part of the impact and redirect the body into the next movement. Airborne movement uses another system hidden deeper inside the skull. Within each inner ear lies the vestibular system, a group of fluid-filled structures that detects head rotation, acceleration, and orientation. When a cat begins to fall with its back facing downward, the vestibular organs signal how the head is moving. The head turns first toward an upright position. Its front legs may draw inward while the rear legs extend, changing how easily the two halves of the body rotate. Physicists describe this property as moment of inertia. A compact body segment turns more easily, while an extended segment resists turning. The cat then changes the limb positions. The front portion slows as the rear portion rotates into alignment. This sequence allows the body to turn without needing a fixed surface to push against. Vision can assist orientation, although it is not the only guide. Blind kittens have been observed developing a mature aerial righting response by about 33 days of age. That finding shows how strongly the movement depends on the vestibular system and the body's sense of its own position. The tail can help with balance during running, climbing, and sudden turns. It also shifts weight as the cat adjusts its posture. Righting remains possible in cats with very short tails or without normal tail control, because the spine and limbs can still change position independently. Landing feet first improves orientation, but it cannot remove the force of impact. Height, landing surface, body position, and physical condition all affect what happens when the paws meet the ground. The reflex guides the body rather than making it immune to injury. On a normal household jump, the same systems operate on a much gentler scale. The rear legs lift the cat toward a shelf. Its spine lengthens in the air. Front paws reach for the surface, then bend as the pads settle. Shoulders slide forward, and the body arrives behind them with barely a pause. The skeleton has carried the cat onto a narrow ledge with precise control. As the muzzle approaches the edge, several long hairs begin to bend before the nose or cheek can touch it. The first point of contact occurs at the tip of a long curved hair. Its technical name is a vibrissa. The plural form is vibrissae. The familiar word whisker is easier to hear, although vibrissae also grow in several places beyond the muzzle. Each exposed shaft is made mainly from keratin, the same tough protein found in claws and ordinary hair. No nerve runs through the length of the shaft. The sensitive structures lie beneath the skin, inside the deep follicle holding its base. When the whisker touches the edge of the ledge, the shaft bends slightly. That small movement applies force to tissues hidden around its root. The specialized structure beneath the skin is called a follicle sinus complex. A sinus in this case is a blood-filled space surrounding part of the follicle. The blood supports the tissues and helps transmit pressure when the whisker moves. clusters of sensory nerve endings sit around the follicle. Some respond when the shaft changes direction. Others detect pressure or vibration within the surrounding tissue. These sensory endings contain mechanoreceptors, which are cells or nerve structures that react to physical force. The process begins with an object pressing against the whisker. Movement travels down the shaft and shifts the follicle within the skin. Soft tissues around the root change shape under that pressure. Mechanoreceptors convert the deformation into electrical nerve signals. Those signals travel toward the brain, where they can be combined with information from nearby whiskers, the skin, the eyes, and the inner ear. This conversion of physical movement into a nerve signal is called mechanical transduction. It allows an external touch to become information the nervous system can use. The whisker acts somewhat like a flexible lever. A light touch near the tip can create a measurable change at the deeper base. The shaft is thickest close to the face and gradually narrows along its length. This taper affects the way bending forces and vibrations travel. Mechanical models of cat family whiskers have compared their natural shape with an imagined rod of equal thickness from base to tip. The tapered form can transmit useful contact information while remaining light and flexible. Its curve and stiffness also affect how the follicle is pushed when the tip meets a surface. A single whisker does not produce a perfect numerical reading of distance. The cat receives a changing pattern from many whiskers moving at once. As the muzzle nears a box opening, several tips may touch at different times. A slight turn of the head changes which shafts bend and how strongly they move. The nervous system can use those differences while guiding the face through the nearby space. The best-known whiskers grow in rows on either side of the muzzle. Cats also carry shorter vibrissae above the eyes, where contact may help protect the face as it approaches an object. Others grow along the cheeks and close to the lips or chin. A less obvious group appears on the backs of the front legs. These are often called carpal whiskers because they grow near the wrist area or carpus. They can provide close-range information when the cat holds an object beneath its chest, where direct vision is limited. Small muscles around the follicles change whisker position. The muzzle whiskers may angle forward during close investigation, or draw nearer to the cheeks in other situations. Their position can contribute to a larger pattern of body language, though one whisker angle cannot identify a precise emotion by itself. Whiskers can also respond to moving air. An object passing nearby disturbs the air around it, and a sensitive shaft may vibrate as that disturbance reaches the face. Air movement provides broad information rather than a detailed image of everything nearby. A popular claim says that a cat's whiskers always match the width of its body and act as a perfect test for narrow openings. The real relationship is less exact. Whisker length varies among individuals. Body weight, thick coats, posture, damaged shafts, and natural differences all affect how well the spread of the whiskers matches the widest part of the body. They still contribute valuable information when the cat approaches a close boundary. Their usefulness comes from patterns of touch and movement, rather than from serving as a fixed measuring tape. Around the muzzle, the nearest few centimeters are therefore crowded with small mechanical events. A cardboard edge bends one shaft. A current of air moves another. Muscles alter their position while the head turns. The ledge beneath the cat has already been examined through a network of flexible levers and sensitive follicles. Beyond whisker distance, the fading room is gathered by eyes built around a different compromise. Across the room, a small amount of light still enters through a window, doorway, or glowing screen. That faint light is enough for the cat's eyes to keep working. Complete darkness is different. Vision requires photons, the tiny packets of energy carried by light. Without photons reaching the eye, neither a cat nor a human can form a visual image. The feline advantage begins when some light remains, even after the room has become too dim for comfortable human sight. Light enters through the clear front surface of the eye and passes through the pupil. A lens focuses it onto the retina, a thin layer of light-sensitive tissue lining the back of the eye. The retina contains two important kinds of photoreceptor cells. Photoreceptors are cells that respond when light reaches them. Rod cells are especially sensitive under dim conditions. They are useful for detecting movement, edges, and changes in brightness. Cone cells work best under stronger light and contribute more to color vision and fine detail. A cat's visual system gives strong priority to rods. That arrangement supports activity at twilight, beneath furniture, or along a garden path after sunset. It also means that the feline eye does not collect every kind of visual information equally well. Cats can see color. The old claim that their world appears only in shades of gray is incorrect. Experiments have shown that cats can distinguish certain wavelengths, which are different parts of the light spectrum. Their color range is more limited than ordinary human vision. Human eyes usually contain 3 working cone systems, producing what scientists call trichromatic vision. Cats appear to rely more heavily on 2 main cone systems. Blues and yellowish tones are easier for them to separate than many reds or greens. Brightness, contrast, and movement often carry more useful information than a rich range of color. Behind much of the feline retina lies a reflective layer called the tapetum lucidum. The name means bright carpet. Light that passes through the retina without being absorbed can strike this layer and reflect forward again. That returning light travels through the photoreceptors for a second opportunity to be detected. The extra pass is especially useful when only a small number of photons enter the eye. Under a microscope, the cat's tapetum appears as several layers of specialized cells. Inside them are organized reflective structures that help send light back through the retina. The same reflection creates the familiar glow seen when headlights, a flashlight, or a camera light reaches a cat's eyes from near the observer's position. Eyeshine may appear green, yellow, or blue-green, depending on the angle, the individual cat, and the light source. The pupil provides another major adjustment. It is the dark opening at the center of the iris. The iris is the colored ring of muscle that controls how wide that opening becomes. In bright sunlight, a cat's pupil can narrow into a thin vertical slit. As the light fades, the iris relaxes and the pupil opens until it becomes broad and nearly round. This wide range allows the same eye to operate in strong daylight and much dimmer evening conditions. Pupil size also responds to signals from the autonomic nervous system, which controls automatic body changes linked with alertness and arousal. A cat watching a fast toy may develop wide pupils even in a well-lit room. Bright light may keep the pupils narrow while the animal remains intensely focused. Their shape therefore needs to be read alongside lighting, posture, and behaviour. Dim light sensitivity carries trade-offs. A cat sees nearby fine detail less clearly than a human with normal vision. Small printed letters, subtle colour differences, and very close objects do not suit the strongest parts of its visual system. Movement at a distance is more important. The room remains usable after human eyes begin losing clear outlines, although it never becomes perfectly bright or sharply detailed. Near the wall, a small object may move just enough for rod-rich vision to notice the change. Once it stops, its shape can merge again with the shadows. A faint sound may then reveal what sight can no longer separate, including frequencies that rise far beyond the upper edge of human hearing. A tiny vibration reaches the air from somewhere near the wall. The cat hears it before the source becomes visible. Sound begins when an object moves and pushes against nearby particles in the air. Those particles press against others, creating a travelling wave. The number of vibration cycles completed each second is called frequency. Frequency is measured in hertz. A sound at 100 hertz completes 100 cycles each second. Higher frequencies contain more cycles within the same amount of time and usually sound higher in pitch. Cats can hear across a remarkably broad range. In a behavioural study published in 1985, 2 cats were trained to respond when they detected tones played through a speaker. At a sound level of 70 decibels, they responded to frequencies from approximately 48 Hz to 85 kHz. 1 kHz equals 1000 Hz. 85 kHz therefore means 85,000 vibration cycles every second. Young humans are commonly described as hearing up to about 20 kHz under good conditions. That upper limit often falls with age because delicate sensory cells inside the inner ear can become less responsive over time. The measured feline range should not be treated as one fixed boundary for every individual. A quiet sound must usually fall within a more sensitive part of the hearing range before it can be detected. Louder sounds may remain audible at frequencies near the edges. Age, ear health, background noise, and individual variation also change the result. Even with those limits, cats hear many high-frequency sounds that remain completely unavailable to human listeners. This ability has practical value for a small predator. Mice and other rodents produce calls containing very high frequencies. Their claws, teeth, and bodies can also create brief rustling or scratching sounds as they move through dry grass, leaves, or narrow spaces. A cat does not need to understand every sound as a complete message. A faint burst of high-frequency energy can reveal that a small animal has shifted position. Useful lower frequencies remain within the cat's hearing range as well. This wide span allows the same ears to detect a deep household vibration, a human voice, and much higher sounds produced by small prey. Ultrasonic simply means that a frequency lies above the usual upper limit of human hearing. The word does not tell us whether a sound is loud, harmless, uncomfortable, or even detectable by a particular cat. Frequency and loudness describe different properties. Once a sound has been detected, the cat still has to locate it. The visible outer ear is called the pinna. Each pinna can rotate toward a source through the action of several small muscles. One ear may turn while the other remains angled in a different direction. The pinnae collect sound and alter it slightly before it enters the ear canals. Their folds change some frequencies more than others, creating a pattern that depends on the sound's direction. The brain also compares what arrives at the left and right ears. A sound coming from the cat's right side reaches the right ear a fraction of a second earlier. The head blocks part of the wave before it reaches the left ear, making some frequencies quieter on that side. Scientists call the arrival time difference an interaural time difference. The loudness difference between the ears is an interaural level difference. Interaural simply means between the ears. Lower frequencies often provide useful timing information because their waves bend around the head more easily. Higher frequencies create stronger loudness differences because the head blocks more of their energy. The shape of each pinna adds further clues about whether a sound came from above, below, ahead, or behind. Experiments measuring the smallest angle cats can distinguish show that the nervous system changes its reliance on these cues across different frequencies. The process happens quickly enough to guide movement without conscious calculation. A pinna turns toward the faint sound. The head follows and brings both ears into a better position. The eyes then align with the estimated location as the shoulders begin to rotate. Hearing has directed the movement system toward a point in space before the hidden source has appeared. The room that seemed quiet contains layers of vibration beyond the human range. Most of those vibrations disappear as soon as their source becomes still. A scent can remain after the footsteps, voice, or moving body that produced it has already disappeared. The faint scratching stops before the cat reaches the wall. No vibration remains in the air, yet chemical traces may still cling to the floor, fabric, or nearby object. Tiny molecules can remain after the animal or person that released them has moved away. Some of these molecules are volatile, meaning they evaporate easily and travel through the air. When the cat breathes in, they enter the nasal passages and reach a folded patch of sensory tissue called the olfactory epithelium. Millions of receptor cells sit within this tissue. Different molecules fit different receptors according to their chemical shape. When a receptor responds, it creates an electrical signal that travels along a nerve fiber toward the brain. Those fibers enter two structures called the olfactory bulbs, positioned near the front of the brain. There, signals from similar receptors gather into organized patterns. The cat's nervous system can compare those patterns with earlier experience, allowing one smell to become familiar, while another holds attention for longer. Chemical learning begins very early in life. Newborn kittens enter the world with closed eyes and limited hearing. Their movements are small, and their ability to control body temperature is still developing. Odor and touch help guide them across the short distance toward their mother's body and nursing area. Warmth, milk, and familiar scent occur together again and again. Through repeated contact, those smells become linked with feeding and a stable resting place. This early dependence shows why scent remains important long after the eyes have opened and the ears have become fully responsive. Cats also possess a second chemical sensing pathway. The main olfactory system is especially useful for volatile molecules carried through the air. A separate structure, called the vomeronasal organ, responds to certain chemicals involved in social and reproductive communication. It lies above the roof of the mouth and connects with passages near the nasal cavity. A cat investigating a strong or unusual scent may pause with its mouth slightly open. The upper lip can lift, and the face may seem briefly frozen. This is called the feline response. Movements of the tongue and mouth help bring chemical material toward the accessory sensory pathway. The response supplies a closer chemical sample. It does not reveal every detail about another animal's mood or intentions. Human scent can also be separated into familiar and unfamiliar patterns. In a study published in 2025, researchers tested 30 domestic cats. Each cat encountered samples collected from a familiar person, an unfamiliar person, and a blank control. The human samples came from behind the ear, the armpit, and the space between the toes. Cats spent an average of about 4.82 seconds sniffing the unfamiliar person's scent. The familiar person's sample received approximately 2.40 seconds of investigation. The blank control was examined for about 1.93 seconds. Longer investigation of the unfamiliar sample supports the idea that cats can distinguish a known human odor from a new one. The experiment measured sniffing time under controlled conditions. It leaves open how scent combines with voice, appearance, movement, and past experience when a cat recognizes a person during ordinary life. A cat can also add chemical information to the surroundings. Glands around the cheeks, lips, forehead, and chin release small amounts of scent material. When the cat presses its face against a chair leg or a familiar hand, the movement combines physical contact with scent deposition. The object becomes part of a repeatedly marked route through the home. Similar rubbing between friendly cats can exchange scent while maintaining close contact. Chemical differences appear in less visible places as well. Cats possess anal sacs near the opening beneath the tail. These sacs release strongly scented material. Controlled experiments have found that cats can distinguish anal sac odors from different individuals, showing that these secretions carry recognizable chemical variation. A doorway may therefore contain traces from a passing flank. The edge of a table can hold material left by a cheek. A blanket may carry skin oils, saliva, and the scent of the person or animal that used it earlier. The room develops a chemical history that changes throughout the day, even when its furniture appears unchanged. Food enters this scented world before it reaches the mouth. Odor may attract the cat toward a bowl, yet taste reveals an even older specialization, shaped by receptors that respond strongly to meat and barely at all to sugar. Odor draws the cat toward the food before the first bite is taken. Once the food enters the mouth, flavor begins through several senses working together. Smell contributes information from molecules traveling into the nose. Temperature changes how strongly some aromas are released. Texture tells the tongue and jaws whether the food is soft, fibrous, smooth, or firm. Taste begins when dissolved chemicals reach receptor cells in small structures across the tongue and mouth. These signals combine in the brain to create the full experience of eating. For a cat, that experience has been shaped by a long dependence on animal prey. Cats are obligate carnivores. The term means that their normal metabolism requires nutrients found naturally in animal tissues. It does not mean that wildcats eat only strips of muscle. A whole mouse or small bird contains organs, connective tissue, fat, bone minerals, and fluid. The digestive tract of prey may also contain small amounts of partly processed plant material. The important point lies in the cat's nutritional needs. Its body developed around a steady supply of compounds that are abundant in other animals. This history can be seen in the way cats taste. Most mammals detect sweetness through a receptor built from two protein parts. One of those parts is called T1R2. The gene that normally provides instructions for making it is written as TAS1R2. In cats, this gene became a pseudogene. A pseudogene is a piece of genetic material that resembles a working gene, but no longer produces a normal functional result. The disabled sweet receptor gene leaves the usual mammalian sugar detector incomplete. As a result, cats are generally indifferent to sweetness. A sugary food may still attract an individual cat because of its fat, smell, salt, temperature, or texture. The sugar itself provides little of the reward that humans experience. Other taste systems remain active. Cats can respond to bitter compounds, acids, salts, and chemicals related to amino acids. Amino acids are the small building blocks used to make proteins. Researchers have identified at least 7 working bitter receptors in cats. These receptors may help detect potentially harmful compounds, although each one responds to a different range of chemicals. Feline receptors linked with savory, protein-rich flavor also respond to combinations of amino acids and nucleotides. Nucleotides are small molecules used in cells and genetic material. They are common in animal tissue and can strengthen the savory taste known as umami. The cat's teeth continue the same carnivorous pattern. An adult normally has 30 teeth. Small incisors line the front of the mouth and can help with delicate biting or grooming. Long canine teeth sit beside them. Their pointed shape is suited to gripping and puncturing. Farther back are premolars and molars with sharp edges. The largest cutting pair forms the carnassial teeth. When the jaws close, these teeth pass beside one another like blades. They shear food into smaller pieces. A cow or horse moves its jaw widely from side to side, while grinding fibrous plants. The cat's jaw is more restricted in that direction. Much of its chewing uses an up and down closing motion. Pieces of food may therefore be cut and swallowed without being ground into a smooth paste. Carnivory also appears in the liver and other organs. Taurine provides one clear example. Taurine is an amino acid-related compound needed for normal vision, heart function, digestion, and other body processes. Many mammals can produce enough taurine from other compounds. Cats make only limited amounts and lose some through normal digestion. Their diet must therefore supply it directly. Vitamin A follows a similar pattern. Many plant-eating or mixed-diet mammals can convert orange and yellow plant pigments, called carotenoids, into active vitamin A. Cats perform that conversion poorly. They depend more directly on preformed vitamin A, which is naturally present in animal tissues, such as the liver. Complete commercial cat foods are formulated with these requirements in mind. Their recipes are designed to provide taurine, active vitamin A, and other nutrients in appropriate amounts. The details belong to metabolism rather than personal taste. A cat does not choose meat because it has studied its nutritional needs. Generations of dependence-shaped receptors, enzymes, teeth, and digestive pathways around the same food source. The mouth now carries a record of that history. Sweetness receives little attention. Protein-related chemicals create stronger signals. Sharp teeth divide animal tissue with a short closing motion. Those structures gain their full purpose when the rest of the body joins them. Eyes, ears, nose, whiskers, claws, and spine begin working as one connected hunting sequence. A faint movement near the floor brings the cat's sensory systems together. The ears may detect a soft rustle before the eyes separate its source from the background. One pinna turns, followed by the head. The pupils widen slightly as the cat fixes its gaze on the moving point. Whiskers angle forward when the face begins to approach. Its body lowers until the chest rests closer to the ground. Bent legs keep the outline small while storing the ability to move quickly. Each padded paw lands with controlled pressure. The claws remain protected, reducing sound as the cat advances. Distance is updated throughout the approach. Movement across the two retinas helps the brain judge direction and speed. Changes in the apparent size of the target provide information about whether it is moving closer. The whiskers become more important during the final approach, when the object enters the space directly around the muzzle and paws. A hunt develops through a chain of linked actions. Detection begins the sequence. Orientation places the head and sensory organs toward the source. Stalking reduces the distance. The rear limbs then fold beneath the pelvis as the muscles prepare to release force. A short chase may follow, or the cat may move directly into a pounce. Front paws reach ahead and attempt to grasp. The claws emerge when extra traction is needed. Teeth can then secure what the paws have caught. Real hunts do not always move through every stage. A sound may stop before the cat locates its source. Prey can disappear during the approach. A pounce may miss, leaving the sequence unfinished. The cat may also pause after grasping and release the object without biting it. These stages are controlled by connected parts of the nervous system, yet each has some independence. That separation explains why a cat may stalk a toy soon after finishing a meal. Food in the stomach reduces immediate hunger, but it does not shut down every movement related to hunting. Searching, chasing, catching, and eating have overlapping forms of motivation. A flicking string can activate visual tracking and pursuit even when the cat has no reason to consume what it catches. Fast motion traveling away from the body is especially effective at drawing attention. A small object moving behind furniture may resemble the interrupted path of prey. The cat can respond to those movement features without mistaking the toy for a living animal in every other way. Play often uses portions of the same sequence. A kitten may crouch behind a chair leg and rush toward a littermate. An adult can bat a toy across the floor, hold it between the front paws, and rake it with the rear feet. The object may be released, watched, and approached again from a new angle. Rear foot raking uses repeated kicks from the powerful hind limbs, while the front paws hold something near the chest. Social play can contain chasing, wrestling, and gentle biting. Its movements often remain looser than a serious conflict, with roles changing as one cat pursues and then becomes the one being pursued. Object play places more attention on capturing and controlling an item. The boundaries can overlap. especially when two kittens chase the same toy. Hunting ability varies greatly among domestic cats. Young kittens must practice control of their paws and timing. Early experience affects how well an animal recognizes prey movements and completes a capture. Outdoor access creates opportunities that an indoor cat may never encounter. Age and physical condition influence speed, hearing, and endurance. Temperament also matters. One cat may watch movement for several minutes without approaching, while another begins chasing almost immediately. Local surroundings change what is available to hunt. A farm may contain rodents around feed storage. A suburban garden can bring insects, birds, or small mammals within reach. On an island, the ecological result may be much greater. Humans have carried domestic cats across oceans to places where native animals developed for thousands or millions of years without similar land predators. Ground nesting birds and small reptiles may have few effective responses to a quiet mammal that stalks low to the ground. The effect differs among locations and individual cats. Some cats rarely hunt, while a smaller number may account for many captures within one area. Vulnerable island ecosystems can still experience serious losses when hunting cats become numerous. The same body that crosses a carpet quietly can therefore influence an environment far beyond the home. Its senses gather movement, muscles convert that information into force, and each stage prepares the one that follows. This concentrated activity usually lasts for a short part of the day. Long periods of waiting, resting, and sleep surround those brief bursts, conserving the body that produces them. After the burst of movement ends, the cat's breathing slows and the limbs settle beneath the body. The ears may remain upright for a while, turning towards small sounds as the muscles relax. This quiet posture can look like sleep, even when the animal is still watching the room. Resting, drowsiness, and physiological sleep are different states. A resting cat may remain fully aware of nearby movement. During drowsiness, the eyelids grow heavier and the head may lower, yet a soft sound can still produce an immediate response. True sleep brings measurable changes in brain activity, muscle tone, breathing, and awareness of the surroundings. Estimates of feline sleep often range from about 12 to 20 hours during each 24-hour period. That broad range includes large differences among cats and between methods of observation. An owner watching from across a room may count several hours of quiet rest as sleep. Researchers using brain recordings or movement sensors can separate some of those states more carefully. Age changes the total as well. Young kittens spend much of the day sleeping, while their nervous systems and bodies develop. Healthy young adults often have longer active periods. Older cats may rest more because movement requires greater effort, or because their daily routines become less demanding. Temperature also affects behaviour. A cat may remain curled up for longer during cold weather, conserving body heat beneath the coat. Very warm conditions can reduce activity during the hottest part of the day. Health, food availability, play, outdoor access, and household noise all influence how much time appears to be spent asleep. Cats are polyphasic sleepers. Polyphasic means that sleep is divided into many separate periods. A human may aim for one long block during the night. A cat commonly moves through repeated cycles of activity, rest, sleep, and waking across the full day. This pattern suits an animal whose hunting opportunities may appear briefly. A rustle in grass or movement near stored food could last only a few seconds. Remaining capable of waking between sleep periods allowed ancestral cats to respond when prey became available. Short sleep bouts also leave room for repeated feeding and regular checks of the environment. Domestic life can rearrange those bouts. A cat may sleep through a quiet afternoon, become active when people return home, then rest again after an evening meal. Another may wake before dawn because birds, outdoor cats, or familiar kitchen sounds become active at that hour. The outer appearance of sleep also changes with depth. During light rest, the paws may remain tucked beneath the chest. The head stays raised or lowers only slightly. Ears can continue turning, and the eyes may remain partly open. A sudden sound may bring the head up at once. Deeper sleep usually brings looser posture and slower responses. The body may stretch onto one side. Muscles supporting the head relax more fully. Breathing becomes steadier, although its exact rhythm can change as sleep stages shift. Inside the skull, electrical activity moves through repeating patterns. Cats pass through non-REM sleep and REM sleep. During non-REM sleep, brain activity generally becomes more synchronized. Large groups of nerve cells begin changing their electrical state together in slower rhythms. This stage includes periods of deeper sleep, when the cat becomes less responsive to ordinary sounds. REM sleep has a different pattern. The letters refer to rapid eye movement. During this stage, the eyes move beneath the closed lids in short clusters. Brain activity becomes more similar in some ways to waking activity. At the same time, most muscles used to hold posture lose much of their normal tone. This reduction helps keep large movements from following every signal produced by the sleeping brain. Small twitches can still appear in the paws, whiskers, ears, or tail. A kitten may show especially visible movements because its developing nervous system produces frequent active sleep periods. These signs support the conclusion that the brain remains highly active during REM sleep. They cannot reveal the exact images or experiences occurring within the sleeping cat. Scientists have studied feline sleep for many decades. Cats played an important role in 20th century experiments that mapped changes in brainwaves, eye movement, and muscle tone during REM sleep. Those studies helped establish sleep as a set of active, alternating neural states. The cat lying motionless is therefore passing through an organized process. Its brain shifts between stages. Muscle control changes, while sensory responsiveness rises and falls. Several sleep bouts can be spread across the day, each fitting around activity and the conditions of the home. The total amount explains how long the cat remains still. Its internal clock helps decide when that stillness ends, and familiar light, meals, and human routines can move an ancient schedule around the hours of the day. The hour of waking depends on more than the amount of sleep already completed. Cats are often described as nocturnal animals. Nocturnal means mainly active during the night. Many domestic cats show stronger activity near dawn and dusk, a pattern called crepuscular activity. Wild rodents and other small prey often become active during these dim hours, when temperatures are cooler and shadows provide cover. The domestic cat remains flexible enough to shift away from that pattern. An indoor cat may sleep through sunrise, become lively after an evening meal, and settle again when the household goes to bed. Outdoor access, local wildlife, age, and individual habit can produce a very different schedule in another cat. Neither nocturnal nor crepuscular serves as a fixed label for every animal. Beneath these changing routines lies an internal timing system. A circadian rhythm is a biological cycle lasting approximately 24 hours. The body generates this rhythm on its own, while signals from the environment keep it aligned with the outside world. Light provides one of the strongest signals. When light reaches the retina, some of that information travels toward timing centers in the brain. These centers help coordinate daily changes in sleep, activity, body temperature, hormone release, and feeding behavior. Morning light can support one pattern of alertness. The fading light of evening helps establish another. Indoor lighting makes the boundary less clear. A bright room may remain illuminated several hours after sunset. Curtains can keep early sunlight from reaching a sleeping cat. Television screens, hallway lamps, and street lights also extend low levels of light into the night. These changes can shift the timing of rest and activity, especially when they occur on a regular schedule. Food provides another powerful cue. A cat that hears the same container open at 7 each morning may begin waiting in the kitchen several minutes earlier. Repeated experience links the hour, household sounds, and the arrival of food. The cat does not need to understand the numbers on a clock. Its internal rhythm combines with learned signals that appear at roughly the same time each day. A caregiver getting out of bed can become part of that sequence. The sound of a car in the driveway may predict someone returning home. An evening toy session can prepare the body for activity. A heating system switching on before sunrise may become another small marker of time. Cats living with dogs or other cats can also adjust to the movement of those animals. This process is called entrainment. Entrainment occurs when repeated outside signals shift or strengthen an internal biological rhythm. Light remains especially important, while meals, play, temperature, and social activity help refine the daily pattern. Several cues may converge late in the evening. A cat wakes after a long rest and stretches its front legs. The back curves, the hind limbs extend, and alertness rises. Stored activity combines with a natural active period and the movement of people around the home. The result may be a sudden sprint through a hallway. This familiar burst is often called the zoomies. A cat may run rapidly across one room, turn around furniture, chase a toy, and stop within less than a minute. Some bursts follow the litter box. Others appear after grooming, social play, or a period of quiet rest. Young cats often show them more frequently because they carry high play motivation and developing movement skills. Adult cats can continue the same behavior when timing, energy, and stimulation come together. No single explanation covers every sprint. The common feature is a quick release of coordinated movement during a period of rising arousal. Sleep may return soon afterward. During REM sleep, the body again enters a state in which the brain remains active, while most postural muscles lose much of their normal tone. Small signals can still reach the paws, ears, tail, or whisker muscles. A paw may flex once against the blanket. The whiskers can shift across the muzzle. Closed eyelids may show brief movements beneath them. These signs fit with active motor circuits during REM sleep. They do not reveal the subject of a dream. A twitch cannot tell us whether the cat is experiencing a hunt, a familiar voice, or a route through the home. The internal clock continues through every sleeping stage. Light and routine keep adjusting it, while repeated household events add their own timing cues. When the cat wakes again, stretching is often followed by a slower and more careful movement. The tongue reaches the shoulder or front leg, carrying saliva through structures that work like a hidden comb. Its first stroke begins when the tongue presses into the fur and pulls backward toward the mouth. The surface feels rough because it carries many small structures called filiform papillae. A papilla is a raised projection on a body surface. These particular papillae are coated in keratin, the same durable protein found in claws and hair. They point toward the back of the mouth, allowing them to catch loose strands as the tongue moves through the coat. Their shape is more complex than a simple solid spike. In 2018, researchers examined grooming tongues from domestic cats and 5 wild members of the cat family. The group included bobcats, cougars, snow leopards, tigers, and lions. High-speed cameras recorded each licking movement. Force sensors measured how the tongue pressed against fur. Medical imaging revealed structures too small to study clearly from the outside. The larger grooming papillae contained a U-shaped hollow near each tip. When the tongue rests inside the mouth, this hollow fills with saliva. The liquid enters through capillary action. Capillary action is the movement of fluid through a narrow space, caused by attraction between the liquid and the surrounding surface. The same process helps water rise through a thin paper towel. As the cat extends its tongue, saliva remains inside the small cavity. Pressure against the coat causes the flexible papilla to rotate until its tip points more directly into the fur. This change in angle allows the hollow end to pass between neighboring hairs. A single grooming stroke can therefore carry saliva beneath the coat's outer surface. Depth matters because cat fur is arranged in layers. Longer guard hairs protect the outside of the coat. Finer hairs beneath them trap air and provide insulation. Loose hair and small pieces of debris can collect among these layers, beyond the reach of a flat tongue surface. The papillae separate tangled strands as they move. Detached hairs become caught on the backward-facing tips and travel toward the mouth. Repeated strokes rearrange the coat so that hairs lie more evenly across the skin. Saliva reaches closer to the roots, where it can loosen material that has collected beneath the visible surface. A front paw helps clean areas the tongue cannot reach directly. The cat licks the paw, then passes the dampened fur across the face and around the ears. Other areas can be reached by bending the spine and rotating the hips. The same flexible skeleton used during a jump also allows the mouth to reach much of the back, sides, and rear legs. Grooming contributes to temperature control as well. Saliva spread across the coat absorbs heat when it evaporates. Evaporation occurs when liquid molecules gain enough energy to leave the surface and enter the air as vapor. That change carries some heat away from the body. The effect can be useful because cats possess relatively few sweat glands across most of their skin. Poor sweating and changes in blood flow also contribute, while grooming adds another route for releasing heat. A washing session can begin for several reasons. Many cats groom soon after waking or eating. Contact with a person or another animal may be followed by licking the touched area. Exploration can leave unfamiliar odors on the coat. Excitement or uncertainty may also be followed by a brief grooming movement. The action remains physically similar even when the event that began it changes. Saliva spread through the coat carries more than moisture. Cats produce a major allergenic protein called FeLD1. After this formal name, it can simply be called the allergen. It is produced in tissues that include salivary glands and glands associated with the skin. Grooming transfers allergen-containing saliva onto the hair. As the coat dries, tiny particles can break away and enter household dust. Movement through bedding, carpet, or furniture can send some of that material into the air. Cat hair helps transport the allergen around the home, while the protein itself causes the immune reaction in sensitive people. The repeating wash now contains several connected processes. Hollow papillae collect saliva, rotate into the fur, and carry moisture beneath the visible coat. Each stroke helps remove loose material while spreading scent and allergenic proteins. Evaporation can release a small amount of body heat. A movement that appears almost automatic is shaped by fluid physics, specialized anatomy, and the layered structure of feline fur. Grooming often remains private maintenance, although licking and rubbing can also appear during social contact. Posture, tail position, eye movement, and distance then change the meaning of the scene. A single gesture provides only part of the message, while the cat's whole body supplies the rest. A cat approaching another living creature sends information through nearly every visible part of its body. The meaning comes from the full arrangement: ear direction, body height, muscle tension, whisker position, tail movement, pupil size, and distance all contribute. Events from the previous few seconds matter as well. A cat entering a familiar room with loose muscles and an upright tail presents a different picture from one standing beside an unfamiliar animal with the same tail held stiffly. The receiver gathers these details together rather than translating one movement in isolation. Ears offer some of the clearest changes. Forward-facing ears often accompany close attention towards something ahead. An ear may rotate sideways to monitor a second sound while the eyes remain fixed on the first source. Flattened ears can reduce their exposed surface and appear during fear, intense conflict, pain, or strong irritation. The rest of the body helps separate those possibilities. A crouched cat, leaning away from something, presents a different context from a playful cat, briefly turning its ears during a fast wrestling movement. Whisker position adds another layer. Whiskers may angle forward as the cat investigates something close to the face. They can draw nearer to the cheeks during withdrawal or defensive tension. Since whiskers also move for practical sensing, their position needs to be considered alongside the muzzle, ears, and direction of travel. The tail is especially easy to notice and easy to misread. A tail held upright commonly appears during friendly approaches. Kittens use this posture when approaching their mother, and adult cats may carry it toward familiar cats or people. The tip sometimes curves slightly as the animal comes closer. A low tail can appear when a cat feels cautious or is moving through an uncertain space. When the hairs stand outward, the tail looks much larger. This reaction is called piloerection. Tiny muscles at the base of the hairs contract automatically during strong arousal, increasing the visible size of the tail and sometimes the fur along the back. Rapid tail movement also requires context. A cat watching a toy may sweep the tip from side to side while judging distance. Broader, forceful motion can occur during frustration or a tense social encounter. Some cats move the tail during energetic play, while others hold it almost still. Speed alone does not supply a complete translation. The eyes bring their own limits to body language reading. Large pupils often appear in dim light because the iris opens the pupil to admit more light. The same widening can occur during excitement, fear, surprise, or intense play through automatic activity in the nervous system. Narrow pupils commonly appear in bright light. A strongly focused cat may also show narrow pupils under certain conditions. Lighting, therefore, needs to be considered before pupil size is treated as an emotional clue. Slow eye narrowing has received closer scientific attention. In a study published in 2020, researchers examined interactions between domestic cats and people. During one experiment, caregivers sat near their cats and slowly narrowed their eyes before closing them briefly. The cats produced more eye narrowing and half blinking during these exchanges than during periods when the caregivers remained present without performing the sequence. A second experiment used an unfamiliar researcher. After the person performed a slow blink, cats were more likely to approach the researcher's outstretched hand than when the same person maintained a neutral expression. These results suggest that slow eye narrowing can take part in calm, positive communication between cats and humans. Every blink still belongs to its immediate setting. A sleepy cat may narrow its eyes because the eyelids are becoming heavy. Bright light can create squinting. Discomfort can also change the eyes, which is why one brief expression cannot serve as a universal message. Careful observation becomes more useful when several signals agree. A relaxed body, forward or gently turned ears, an upright tail, and slow eye narrowing can form a consistent social pattern. Greater distance, lowered posture, tense muscles, and ears held back create a different picture. Attention to these combinations allows a person to respond more accurately without inventing a complete human thought for the animal. The visible conversation can continue for several seconds without a sound. A closed door, a dark hallway, or a person facing away removes much of that visual channel. Under those conditions, the cat's voice takes on a different job. A sound can cross a doorway when posture and eye movement cannot. Cats produce a wide range of calls, and researchers often group them by how the mouth moves during the sound. Some are made with the mouth closed. Purring belongs in this group, along with soft trills that can sound like a rolling greeting. Many meows begin as the mouth opens and change as it closes again. More intense calls may be produced with the mouth held open for longer. Modern reviews describe roughly 21 named feline vocalization types, although researchers do not always use the same labels or divide the sounds in exactly the same way. A cat's voice is created when air moves through the throat and makes tissues vibrate. Changes in muscle tension alter pitch. The shape of the mouth and throat changes resonance, which is the way certain sound frequencies become stronger. A call can therefore become shorter, longer, lower, higher, smoother, or more broken, without turning into a completely different kind of sound. The domestic meow has become especially important in communication with people. Adult cats do not usually meow at friendly adult cats as often as they meow toward humans. Kittens call to their mother, but many adult house cats continue using meow-like sounds throughout life because those sounds receive useful responses from people. A person may open a door, place down food, begin play, or offer attention after hearing one. Repeated results can strengthen the behaviour. No fixed dictionary explains every meow. Pitch changes from one call to another. Duration may range from a short chirp to a drawn-out sound. Some cats repeat the call several times, while others give one and wait. The melody can rise, fall, or change partway through. Context supplies much of the meaning. A meow beside an empty bowl occurs in a different setting from the same sound beside a closed bedroom door. Familiarity also matters. People living with one cat often learn small patterns in its voice. They may recognize the call used before breakfast or the sound made when a favorite toy has rolled under furniture. Those learned household signals do not always transfer to an unfamiliar cat. In one study, 225 people listened to recordings from cats they did not know. The calls had been recorded during food waiting, isolation, or brushing. Fewer than half of the listeners correctly matched the representative meows to the situations in which they occurred. The result did not make the calls meaningless. It showed that much of their usefulness depends on context, repeated exposure, and knowledge of the individual animal. Purring appears simple because of its steady rhythm, yet it also occurs in more than one situation. Cats often purr while resting near a familiar person or receiving gentle contact. The sound can also appear during food solicitation, stress, physical discomfort, or other high-need moments. Air moves through the vocal system during both inhalation and exhalation, allowing the vibration to continue with only a small interruption between breaths. A purr used while asking for food may contain a higher frequency element mixed into the lower vibration. Human listeners often judge this added component as more urgent. The effect resembles a faint cry placed inside the purr, although each cat produces it differently. Purring therefore needs the same contextual care as tail movement or pupil size. A relaxed body, soft eyes, and comfortable contact support one interpretation. Tension, hiding, reduced movement, or an unfamiliar setting may support another. The sound becomes informative when it is read together with the rest of the animal. Researchers continue to measure feline calls through pitch, duration, rhythm, and changes in frequency. Computer analysis can compare recordings more precisely than the human ear alone. These methods may reveal how strongly a call reflects the individual cat, the immediate situation, or the person being addressed. Even without a complete translation, cat and humans can learn one another's patterns. A particular meow can bring a person toward the kitchen. A soft trill may begin an approach. The human voice can become equally familiar in return. Its tone, timing, and repeated connection with daily events allow certain sounds to gain meaning. The spoken name, the opening of a container, and familiar footsteps approaching through the hall all become part of what the cat has learned. Repeated events gradually turn an unfamiliar building into a predictable place. Footsteps in a hallway may regularly come just before a door opens. A cupboard hinge can predict the arrival of food. The sight of a carrier may become linked with travel. A particular phrase can signal that a toy is about to appear. The voice of one person may lead to touch, play, or a familiar place on the sofa. This process is called associative learning. One event gains meaning because it repeatedly occurs before another. The sound itself does not need to resemble the result. A metal lid has no natural connection with dinner, yet enough pairings can make the smallest click bring a cat into the kitchen. Memory stores part of that relationship, allowing the cue to shape behaviour on a later day. Spoken names can become meaningful in a similar way. In 2019, researchers tested whether domestic cats could separate their own names from other spoken words. The method used two processes called habituation and dishabituation. Habituation occurs when a repeated signal produces less response because nothing important changes. Dishabituation appears when a new or meaningful signal causes attention to rise again. During the experiment, cats heard 4 nouns or other cats' names spoken one after another. Early sounds might cause an ear turn, head movement, or small change in posture. Those reactions usually weakened as the sequence continued. The cat's own name was then played. Many household cats showed renewed orientation, suggesting that they had separated its sound pattern from the words that came before it. The effect also appeared when an unfamiliar person spoke the name. The result shows discrimination of a familiar sound sequence. It does not tell us that a cat thinks of the name as a human does, with a full, abstract idea of personal identity. Repeated consequences may be enough to give the sound special importance. The name can precede food, touch, correction, play, or a person approaching. A familiar voice carries additional information. Cats have responded differently to recordings of their caregiver and an unfamiliar speaker. Their reactions can be easy to miss. An ear may rotate toward the sound. The head can lift briefly before settling again. Some cats change their gaze without moving from the resting place. Recognition, therefore, does not always produce an approach. A cat may know who is speaking while remaining warm, comfortable, cautious, or occupied. Human experiments often reward visible action, although feline knowledge may appear through much smaller movements. Voice can also help a cat track where a person is located. A study published in 2021 used speakers placed in different parts of a room. Cats first heard their caregiver calling from one location. The same recorded voice then appeared suddenly from a second speaker farther away. Independent observers rated the cats as showing greater surprise when the familiar person seemed to move between locations without crossing the space. The reaction was weaker or different when the sounds were less socially important. Evidence from this experiment suggests that cats formed a mental representation of the unseen caregiver's location. A mental representation is an internal idea of where something should be, even when it cannot currently be seen. The unexpected voice conflicted with that stored position. Such experiments require careful interpretation because cat behaviour changes with the setting. An unfamiliar room may reduce exploration. Hunger can increase attention to food-related signals, Fear may keep the body still, even when the sound has been recognized. Previous training affects whether a cat looks toward a speaker, walks to it, or waits for more information. Temperament also shapes the response. One individual may investigate every new object. Another gathers information from several meters away. A short test captures only a small part of those differences. Inside an ordinary home, learning continues over months and years. The cat remembers routes between rooms, the location of water, and the surface where sunlight appears in the afternoon. It learns which doors open, which voices predict contact, and how long a person usually remains away. Furniture can move and routines can change, forcing old expectations to be updated. The building becomes familiar through thousands of small pairings between sounds, places, people, and outcomes. That learning machinery is shared across the species, yet its results differ from one animal to another. The same visitor may draw one cat toward the doorway, while another watches from beneath a table. Each response grows from inherited tendencies combined with a personal history that began early in life. Differences between adult cats begin long before either animal meets a visitor at the doorway. Each kitten starts with a particular genetic mixture inherited from its parents. Those genes influence body size, coat, sensory development, activity level, and parts of the nervous system involved in fear or exploration. Conditions before birth can also affect development. Nutrition, illness, and stress experienced by the mother may influence the environment in which the kittens grow, although later behaviour cannot be traced to one prenatal event with certainty. After birth, maternal care becomes one of the kitten's earliest sources of information. The mother provides warmth, milk, grooming, and physical contact. Her reactions to unfamiliar sounds or approaching people may also shape what the kittens experience during their first weeks. A calm mother who remains nearby during gentle handling creates a different setting from one who retreats or becomes tense. The number of littermates changes daily experience as well. A kitten in a larger litter spends more time competing for space around the mother and interacting with several moving bodies. Littermates provide early practice in chasing, wrestling, biting gently, and stopping when another kitten reacts. These exchanges help refine balance, paw control, and the force used during play. Human contact becomes especially important during a period commonly placed between about 2 and 7 weeks of age. This is often called the early socialization window. During these weeks, the nervous system is highly receptive to information about which sights, sounds, smells, and living creatures belong in the ordinary environment. Gentle handling by several people can make later human contact easier. Short sessions may include being touched around the paws, hearing different voices, or exploring a safe room with unfamiliar objects. Variety matters because a kitten that meets only one person may react differently when someone taller, louder, or less familiar appears later. The contact needs to remain calm and non-forced. Overwhelming a kitten can teach avoidance, just as repeated pleasant handling can support approach. Limited exposure during this early window may make adjustment harder, especially for kittens raised with little human contact. Learning still continues after 7 weeks. Older kittens and adult cats can form new associations, become comfortable with people, and adjust to unfamiliar homes. The early period carries extra influence because so many brain systems are developing at once. yet it does not create an unchangeable adult future. Researchers use the word temperament for behavioral differences that remain somewhat stable across time or situations. A bold cat may approach unfamiliar objects more quickly than a cautious one. Sociability can appear in the amount of contact an individual seeks from people or other cats. Activity level affects how often the animal explores, plays, or moves through the environment. Studies also examine fearfulness, impulsive reactions, and responses to novelty. These traits can overlap. A highly active cat may investigate a new room quickly, while another active cat runs only after the surroundings feel safe. A review covering work published from 1986 through 2020 identified 43 original studies of feline temperament. Researchers used owner questionnaires, direct observation, and controlled tests involving unfamiliar objects or people. The growing number of studies shows that cat personality can be measured, although methods still differ enough to make some findings difficult to compare. Individuality can appear in movements much smaller than approaching a stranger. Some cats repeatedly favor one paw when reaching into a narrow container or holding an object. This side preference is called laterality. Laterality means that one side of the body is used more often or more effectively for a particular task. Several studies have found population-level differences between male and female cats, with males showing stronger left paw use in some tasks, and females showing more right paw use. The pattern depends on the action being tested. Walking downstairs may produce a different result from reaching for food. Many cats show only a weak preference, and some use both sides almost evenly. A paw reaching into a container therefore carries a small part of the same developmental story found in larger behaviours. Inherited tendencies influence how a kitten reacts to experience. Repeated experience then changes what the animal expects from people, objects, and places. By adulthood, each cat has followed a slightly different path through handling, play, household sounds, other animals, and unfamiliar events. Those different histories shape how closely a cat approaches others, how long it remains nearby, and which kinds of company feel comfortable. Some individuals seek frequent contact. Others control the distance carefully or form stable social groups only when food, space, and familiarity make group life worthwhile. The distance a cat prefers from others is shaped by more than personality alone. Its wild ancestors often hunted small prey by themselves. A single mouse or bird rarely provided enough food for a large group, so solitary searching reduced competition. Hunting alone still left room for social contact. Domestic cats can live with little company, form stable groups, or move between those arrangements as conditions change. Food distribution has a strong influence. When prey is scattered across a wide landscape, each hunter benefits from covering its own area. When food gathers in one place, repeated contact becomes easier to tolerate. Fishing docks, barns, markets, and household feeding sites can all support several cats within a relatively small space. Free-ranging groups often form around related females. A mother may remain near her adult daughters. Sisters can raise kittens within overlapping areas. Young cats grow up among relatives whose scents and movements have been familiar since birth. Males may visit, remain at the edge of the group, or travel across several territories depending on food, breeding opportunities, and local population density. These groups do not operate like tightly organized wolf packs. Their home ranges may overlap without every member traveling or hunting together. One cat can rest near a feeding site, while another patrols a nearby building. Relationships form within the larger group, and some pairs spend far more time together than others. Friendly behaviour can be seen in several clear movements. A cat may approach another with the tail held upright. The two animals can pause for a brief nose-to-nose investigation. Rubbing transfers scent, while bringing their bodies into close contact. Some familiar cats groom the head or neck of a companion, especially in places that are harder to reach alone. Tails may touch or curl together, while the animals stand nearby. Play can involve chasing or wrestling with loose movement and frequent pauses. Resting in contact provides stronger evidence of social comfort, because sleep reduces immediate readiness to move away. Cats may also choose separate beds only a short distance apart. Physical contact is therefore one sign among several. Living in the same house does not guarantee a close relationship. Two cats can share an address while carefully avoiding one another. One may use the upper shelves while the other stays near the floor. Their feeding times can separate naturally if one waits until the other leaves. A narrow doorway may become difficult when one cat regularly sits beside it. Another cat may delay entering a room until the route is clear. These quiet patterns can continue without loud conflict. The absence of chasing or fighting gives only part of the picture. Comfort is better judged through access to space, relaxed movement, normal feeding, and the freedom to approach or withdraw. A home can therefore contain several invisible territories. One cat may claim the sunny windowsill during the morning. Another uses it later in the afternoon. Separate routes through furniture allow both animals to reach food, water, resting places, and litter areas without repeated close encounters. Height increases those choices because shelves and furniture create additional pathways above the floor. Cats extend the same flexible social behavior toward people. A tail-up approach can greet a familiar human at the door. Cheek rubbing combines touch with scent. Some cats follow a person from room to room while remaining just beyond arm's reach. Others climb into direct contact and settle against a leg or chest. Play, meowing, slow eye narrowing, and sleeping nearby can all become parts of a particular relationship. The amount of contact desired differs across individuals and can change during the day. A cat may seek attention after waking, then choose a quiet shelf once grooming is complete. Age, early socialization, health, household noise, and past experience all influence those choices. This flexibility gives proximity greater meaning. A cat capable of increasing distance has selected a closer place instead. The choice may last only a few minutes, yet it reflects familiarity, opportunity, and a history of safe outcomes. Domestic cats remain independent in many parts of their behavior. They can hunt alone, choose their own resting sites, and control when contact begins or ends. That independence exists alongside the ability to build selective relationships with cats and humans. The combination helped cats live near people without requiring the tightly directed cooperation seen in many working animals. long before a cat slept beside a person or waited at a kitchen door. Wildcats were making smaller decisions about distance. Human settlements gathered food into concentrated spaces. Stored grain attracted rodents, and those rodents created a reason for certain wildcats to remain nearby. The modern home begins far behind the sofa, among early fields, grain stores, and villages, where repeated tolerance slowly became a shared history. Early villages changed the landscape in ways that no wildcat could have anticipated. As people began growing crops, harvested grain had to be stored between seasons. Wheat, barley, and other seeds collected in baskets, clay containers, pits, and simple buildings. These concentrated food stores attracted mice and other small rodents. A settlement could therefore offer a hunting ground richer than the surrounding fields. Wildcats approaching the outer edges found prey gathered into a smaller area. Individuals willing to remain near human voices, smoke, tools, and movement gained access to that food. More fearful cats may have stayed farther away. Over many generations, repeated differences in behaviour could affect which animals survived and reproduced near settlements. People also received a benefit. Rodents consumed grain and contaminated stores. A small predator hunting around walls and storage areas reduced some of that pressure without needing to be trained. Tolerance could grow before anyone deliberately tried to create a domestic cat. This kind of pathway is called commensal domestication. In a commensal relationship, one species benefits from the environment created by another. The partnership can begin without a formal exchange or conscious plan. Cats may have moved toward people through their own feeding choices. That history differs from animals first managed through tighter human control. Livestock were bred for useful products such as meat, milk, fiber, or labor. Dogs were selected over long periods for cooperation in guarding, hunting, herding, and transport. The earliest cats may have needed only access, tolerance, and enough safety to remain close. A less fearful wildcat could hunt near a grain store and leave again. Its offspring might grow up hearing people and moving through the same settlement edges. Familiarity would accumulate through repeated exposure rather than through immediate ownership. One of the most striking early discoveries comes from the island of Cyprus. At a settlement called Shilorakambos, archaeologists uncovered a human burial beside the remains of a cat. The burial dates to roughly 9,500 years ago. The two bodies had been placed only about 40 centimeters apart. That distance suggests deliberate placement rather than an accidental animal death somewhere nearby. The location matters because wildcats were not naturally native to Cyprus. The island lies in the eastern Mediterranean and had no land bridge bringing cats across on their own. A person must therefore have transported the animal, or one of its recent ancestors, by boat. Moving a cat across open water required enough human interest to include it among limited cargo. The burial shows that the relationship had already gained unusual importance by that time. It still leaves several questions open. The animal may have been tame, managed, or socially valued. Its bones alone cannot confirm that it belonged to the exact domestic population from which modern house cats descend. Early domestic cats looked extremely similar to wildcats. Their skulls, teeth, and limb bones often overlap in size and shape. A small wildcat and an early domestic cat can therefore leave remains that are difficult to separate by appearance. archaeologists combine several forms of evidence to improve the picture. Bone measurements may suggest body size and population differences. Burial position reveals how people treated the animal. Radiocarbon dating estimates when the remains entered the ground by measuring the decay of radioactive carbon. Isotopes, which are different forms of the same chemical element, can offer clues about diet and movement. Genetic evidence adds another layer. Mitochondrial DNA comes from structures inside cells that release energy. It passes mainly through the maternal line and often survives in ancient material because each cell contains many copies. Nuclear DNA comes from the cell nucleus and represents far more of the animal's ancestry. It is harder to recover from old remains, especially in warm climates where DNA breaks down quickly. Together, these methods help separate plausible stories from demonstrated history. The grain store pathway remains a strong explanation because it connects human agriculture, rodent abundance, and wildcat behaviour through a clear ecological chain. Its exact timing and location remain less certain. A cat found near people may have been a local wild animal, a tolerated hunter, or part of a population already changing through generations of close contact. For many years, the most familiar account carried domestic cats from early Near Eastern farms into Europe alongside the first farmers. Ancient nuclear DNA has now disrupted that straight route and pointed toward a later arrival from North Africa. For many years, the leading account placed domestic cats in Europe much earlier than the Roman period. Older genetic evidence suggested that cats linked with the Near East traveled west beside Neolithic farmers around 6,000 to 7,000 years ago. Neolithic means the later Stone Age, when agriculture and permanent settlements became widespread across parts of Europe. That account relied heavily on mitochondrial DNA. Mitochondria are tiny structures inside cells that help release energy. They carry a small amount of their own DNA, passed mainly from a mother to her offspring. Each cell contains many mitochondria, so this genetic material is often easier to recover from ancient bones than DNA stored in the cell nucleus. Its survival made mitochondrial DNA extremely valuable to archaeology. It still records only one narrow maternal line. Two populations can share similar mitochondrial branches, even when the rest of their ancestry differs. The nuclear genome contains DNA inherited from both parents and represents a much larger portion of an animal's history. Recovering it from old cat remains is difficult. Heat, water, soil chemistry, and time break DNA into shorter fragments. Researchers must also separate genuine ancient material from modern contamination. A major study published in 2025 used improved methods to examine this broader genetic record. The project gathered cat remains from 97 archaeological sites across Europe and the Near East. Researchers screened hundreds of specimens collected from settlements, burials, ports, and other historical locations. The published comparison included 87 ancient and modern cat genomes. Institutions involved in the work also described 70 newly produced ancient genomes from the larger collection. These numbers refer to different stages of the project, including the remains first examined, and the genomes complete enough for detailed comparison. Nuclear DNA allowed researchers to distinguish more clearly among European wildcats, African wildcats, and domestic cat populations. The result changed the older European timeline. Early cats found at Neolithic sites in Europe were genetically European wildcats. They did not form the main ancestral population of today's European house cats. Some may have lived near settlements and hunted rodents around human food stores. Their presence beside people did not lead directly to the modern domestic populations spread across Europe. The genetic record revealed at least 2 later movements from North Africa. One brought African wildcats to Sardinia around 2,200 years ago. Sardinia is a large island in the western Mediterranean, west of the Italian peninsula. Those animals helped establish the wild-living feline population found on the island. A separate North African lineage reached continental Europe by around 2,000 years ago. This later population became a major genetic foundation for modern European domestic cats. Its genomes showed a closer connection with North African wildcats than with wildcat populations from the Levant, the eastern Mediterranean region once central to the older account. The timing places this movement near the height of Roman expansion. By the first centuries before and after the beginning of the Common Era, Mediterranean ships were carrying grain, ceramics, metals, people, and animals between busy ports. Stored food aboard a vessel attracted mice and rats. A cat hunting below deck could protect part of the cargo during a voyage lasting days or weeks. Ports then gave traveling cats access to warehouses, markets, military settlements, and roads leading inland. Roman trade networks linked North Africa with Italy, Iberia, Gaul, and distant parts of the empire. Cats may have traveled intentionally as pest control. Some probably moved with cargo or settled around port food stores after arrival. Their cultural value in parts of North Africa may also have influenced which animals people chose to transport. Genomes reveal when related populations appeared and where their closest ancestry lay. They rarely preserve the exact reason one particular cat entered one particular ship. The new evidence clarifies the spread into Europe, while leaving the first stages of domestication less certain. Ancient DNA from North Africa remains limited, partly because warm climates speed the decay of genetic material. More remains are needed from Egypt, the Maghreb, and neighboring regions. The Maghreb includes the northwestern part of Africa, including modern Morocco, Algeria, and Tunisia. Strong conclusions will require directly dated bones, detailed archaeological settings, and comparisons among wildcats, tolerated settlement hunters, and animals already living under closer human care. A future discovery could shift the map again. For now, the domestic cat's European arrival appears tied to North African ancestry, Mediterranean shipping, and movement during the Roman age. Across those long journeys, its basic feline body changed remarkably little. Much of the striking variation visible in modern homes appeared closer to the surface, where genes reorganized color, markings, and the growth of the coat. Within each modern cat, the journey through ancient populations is carried inside nearly every cell. Domestic cats normally have 38 chromosomes. These are arranged in 19 pairs, with one chromosome in each pair inherited from the mother and the other from the father. One pair consists of the sex chromosomes. Most females carry 2 X chromosomes, while most males carry 1 X and 1 Y. The remaining chromosome pairs contain thousands of genes involved in building and maintaining the body. Some genes control which pigment molecules a hair produces. Others influence where pigment-making cells travel during development. Additional genetic instructions create boundaries across the skin or switch pigment production as each hair grows. The final coat appears on the outside, although its pattern begins much earlier at the level of cells. Tortoiseshell and calico cats provide one of the clearest examples. Their orange coloring is connected to a region on the X chromosome. A female kitten usually receives one X chromosome from each parent. If one X carries a version linked with orange pigment and the other carries a version linked with darker pigment, both possibilities exist within the same developing animal. Early in embryonic growth, each cell largely shuts down one of its two X chromosomes. This process is called X chromosome inactivation. The choice occurs separately in different early cells. As those cells divide, their descendants usually keep the same X chromosome active. One patch of skin may therefore develop from cells using the orange-related version. A neighboring patch may use the darker version. The visible coat becomes a mosaic, meaning that groups of genetically different active cells form separate areas across one body. Tortoiseshell coats often blend orange and dark patches closely together. Calico coats usually include white areas as well. White spotting develops when some regions of skin receive few or no mature pigment-producing cells. Those pale regions can separate the orange and dark areas, creating the larger blocks commonly seen in calico cats. This X-linked mechanism explains why most tortoiseshell and calico cats are female. Rare males can still occur through unusual chromosome arrangements, genetic changes, or early developmental events. Their rarity follows from chromosome biology, rather than from coat color being completely impossible in a male. Tabby markings arise through a different process. The pattern begins before visible fur covers the kitten. During skin development, chemical signals divide the surface into regions that will later produce different amounts or types of pigment. A gene called DKK4 helps organize some of these early boundaries. After this formal name, it can simply be called the pattern organizing gene. Its activity differs across developing skin, helping establish where darker and lighter regions will appear. Later pigment systems follow that early map. The result may become narrow stripes, broad swirls, broken spots, or a mixture shaped by several genes. Even cats that appear solid-colored carry parts of the basic tabby system. Other genetic effects can hide the markings or reduce their contrast. Under strong light, faint stripes sometimes become visible on the legs, face, or tail of an otherwise dark-looking cat. Each hair can also change color along its length. Pigment may be produced strongly for part of the growth period and then reduced, creating bands within a single strand. Millions of banded hairs combine to form the larger patterns seen across the body. Siamese-type color points reveal how temperature can enter the same process. Dark pigment, called melanin, is produced through a series of chemical reactions. One important enzyme in that pathway is tyrosinase. An enzyme is a protein that helps a chemical reaction happen more easily. In color-pointed cats, a genetic change makes tyrosinase work better at cooler temperatures and less effectively in warmer tissue. The ears, muzzle, lower legs, and tail usually remain cooler than the center of the body. those areas produce more dark pigment. The chest and abdomen stay warmer, so the coat there develops a lighter shade. A kitten grows inside the evenly warm environment of the uterus. Siamese kittens are therefore born pale, with little contrast between the body and the future points. As the ears and other outer regions cool after birth, darker pigment gradually appears. The points become clearer over the following weeks. Age and surroundings can continue changing the result. A cat living in a cooler climate may develop a darker body than a genetically similar cat kept in warmer conditions. Older color-pointed cats also commonly become darker as circulation, body condition, and temperature patterns change. The coat is therefore a record of chromosome activity, developing skin, and local chemistry. Its colors do not provide a reliable guide to personality. They show how cells in different locations follow different genetic instructions while building one animal. Genes establish the coat and much of the body beneath it. Daily surroundings determine where that body can climb, scratch, hide, watch, play, and rest. The cat's environment has now narrowed from ancient ports and grain stores to the walls, shelves, windows, routines, and limited floor space of the modern home. Inside a home, the cat's inherited abilities meet walls, furniture, doors, and human schedules. Digitigrade feet still look for stable roots. Flexible shoulders and a mobile spine make climbing possible. Whiskers continue testing close edges, while the eyes and ears monitor spaces farther away. Scent marks familiar pathways through rooms that may appear unchanged to a person. The hunting system remains ready to follow movement, and sleep still depends on finding places where the body can settle without frequent disturbance. The quality of an indoor environment, therefore, depends on more than floor area. Cats use height as part of their territory. A shelf 1 meter above the ground can provide a different experience from the floor directly beneath it. From an elevated position, a cat can watch a doorway, follow movement across a room, or rest beyond the reach of a dog or young child. Height also creates alternate travel routes. One cat may cross a room along furniture while another remains below. That separation can reduce forced contact in a multi-cat household. A raised bed, window ledge, or sturdy climbing structure can offer visibility. A covered space nearby provides concealment. Access to both gives the animal some control over whether it watches openly or withdraws. Choice matters because a cat cannot always change the room itself. It can only choose among the roots and resting places available within it. Food bowls, water, litter areas, scratching surfaces, and beds also affect how animals move through shared space. When every important resource sits in one small area, cats may be forced to pass one another repeatedly. Separating those resources creates more than convenience. It allows one animal to eat or rest without another controlling the same narrow route. Scratching belongs to this same environmental fit. A cat reaching upward against a rough surface stretches the front limbs and lengthens the back. The claws catch the material and pull downward. This movement helps loosen older outer claw layers, which may later appear as thin, hollow pieces on the floor. The scratch also leaves a visible mark. Scent from glands around the paws adds chemical information to the same location. Many cats scratch after waking, when the muscles begin moving again. Frequently used pathways and areas near resting places can become preferred sites. Surface material changes the result. Some cats favor rough fabric. Others use cardboard, wood, or a horizontal mat. The direction matters too, since one individual may prefer reaching upward, while another scratches along the floor. The behaviour follows normal anatomy and communication, rather than a plan to damage furniture. Play gives the hunting system a safer outlet. A satisfying sequence begins before the final pounce. The cat may first search for movement, then pause to watch. A toy disappearing behind a chair creates an opportunity to stalk. Short bursts of motion can lead into chasing and grasping. Successful capture matters because a sequence with no possible ending can lose some of its value. A toy that remains forever beyond reach provides movement without completion. Allowing the cat to catch it briefly gives the paws and mouth a final point of contact. Individual preference changes the best form of play. A young cat may enjoy fast movement across a long distance. An older cat may prefer slower motion close to a hiding place. Some cats focus on objects traveling along the ground, while others respond more strongly to movement above them. Age gradually changes how the same environment is used. Jumping may become less frequent as joints stiffen or muscles lose strength. Routes can shift toward lower furniture and shorter gaps. Sleep and quiet rest often increase. Grooming may become less complete if bending becomes difficult. Hearing and vision can also change, affecting how quickly the cat notices movement or sound. These changes often develop slowly enough to escape casual observation. In one study, 61 cats living with their owners wore activity monitors. The devices recorded movement through accelerometers, which are sensors that measure changes in speed and direction. Older cats showed less jumping and lower total activity. Their recorded time spent resting and sleeping increased. A monitor cannot explain every cause, but it can reveal patterns that a person might miss when changes happen over many months. A sudden or lasting change still deserves attention, rather than being blamed automatically on age. The modern home works best when it allows an ancient body to keep using its abilities safely. Height offers distance. Scratching gives the claws and muscles a normal task. Play completes parts of the hunting sequence, while quiet, resting places support the long periods of sleep built into feline life. Care becomes more accurate when the room is viewed through the cat's senses and movements. Even careful observation leaves much unseen. Researchers are now using wearable sensors, sound analysis, facial coding, and ancient genomes to measure parts of feline life that human eyes and ears can easily overlook. Those new tools matter because ordinary observation captures only part of a cat's life. Cats have received less behavioral and cognitive research attention than dogs in several important areas. Dogs often tolerate repeated training tasks and unfamiliar laboratories more easily. A cat moved into a strange room may freeze, hide, or spend the test inspecting the surroundings. That response can make it difficult to separate what the animal understands from how it feels about the setting. Feline reactions are also easy to overlook. Recognition may appear as a small ear turn rather than a full approach. Surprise can last only a second. A change in attention may involve the eyes, whiskers, or angle of the head, while the rest of the body remains still. Research programs devoted to dogs have also existed for longer in many universities. Cats were so common in homes that people sometimes assumed they already understood them. Familiarity created confidence before controlled experiments had measured many basic abilities. Important gaps remain in feline perception, memory, physical reasoning, and social behaviour. Researchers still have much to learn about how cats combine scent with sound, remember hidden objects, judge human attention, or represent routes through familiar places. Wearable sensors provide one way to observe behaviour without moving the animal into a laboratory. An accelerometer measures changes in movement along different directions. Similar sensors help a mobile phone detect whether it has been turned or lifted. Attached safely to a collar, an accelerometer can record patterns of running, resting, grooming, and jumping. Some devices also contain air pressure sensors. Air pressure changes slightly with height, allowing the system to estimate when a cat moves from the floor onto a chair or higher shelf. A few minutes of observation may miss a gradual decline in jumping. Continuous recordings across several weeks can reveal a slow shift toward lower roots and longer resting periods. The same data can help researchers compare daytime activity with movement after dark. These sensors measure motion rather than emotion. A period of stillness could represent sleep, quiet watching, or hiding. Accurate interpretation still requires information about the cat's health, surroundings, and normal routine. Computer analysis is extending observation in other directions. Researchers can divide facial expression into measurable movements involving the ears, eyelids, muzzle, whisker pads, and head position. A camera recording several cats can capture changes too fast or subtle for a person to score reliably in real time. Software can compare how often particular movements appear during play, greeting, tension, or resting contact. Sound analysis breaks a meow or purr into pitch, duration, rhythm, and changes in frequency. Machine learning systems can search large collections of recordings for repeating patterns. They may discover features that human listeners miss. These systems still require careful testing, and they do not turn a private feline experience into spoken sentences. Genetics provides an equally clear lesson in scientific caution. The 2025 Ancient Genome Study changed a familiar account of how domestic cats reached Europe. Earlier evidence had supported movement with Neolithic farmers several thousand years earlier. Nuclear DNA instead pointed toward a major arrival from North Africa around the Roman period. Better evidence changed the historical map. Future remains from Egypt, the Maghreb, and surrounding regions may change it again. Improved genomes could also identify more inherited coat traits or health-related variants. Long-term home monitoring may clarify how sleep and movement change with age. Behavioral studies could show more precisely how scent, voice, memory, and location become one familiar person. The cat resting nearby now looks much as it did at the beginning. Its paws may be folded beneath a body balanced naturally on the toes. Curved claws remain lifted away from the floor. Whisker shafts rest above deep sensory follicles, ready to carry the slightest bend into the nervous system. The ears can still detect frequencies beyond human hearing. Behind each retina, a reflective tapetum waits for dim light. Patterns across the coat preserve decisions made by chromosomes, developing cells, and local temperature. Within the sleeping brain, neural activity continues to move between non-REM sleep and REM sleep. The body carries ancestry from African wildcats, while its daily schedule has adjusted to familiar meals, household light, voices, and movement. Sharing a home has made the animal close without making every part of its experience available to us. Scientific understanding grows through patient measurement, comparison, and a willingness to revise earlier conclusions. That process makes affection more attentive. The resting cat remains a real animal with senses, history, and private biological activity, continuing beyond human notice. One ear turns briefly toward a distant sound. Breathing lifts the chest and lowers it again. A few whiskers shift as the internal clock moves quietly through the night. The familiar shape has not changed since the opening moments. Only the amount now visible within it has changed.